Okay, good morning. Almost at the end of this class, not just the quarter. Quarter still has 2 weeks, but we're almost at the end of the class. So today we'll talk about AC power, the last remaining topic and chapter, kind of an important one. I'll keep saying important for all of them. And then next Monday, of course, is a holiday. You have a long weekend coming up. I don't know about you, but I plan to get caught up on my grading work. So hopefully you all have some time to relax too. We'll meet on Tuesday and then on Wednesday again. Tuesday will be quiz number 8. And then there'll be one more quiz number 9, the following Monday. That'll be based on this topic that we are covering today and then next week, which is AC power. Okay. Also, once I cover this topic in quiz 9 or assess this topic in quiz 9, I will not assess it again in the final exam. So you have one shot at getting it done. But we have plenty of time. Okay, we have plenty of time to get through it. Okay, so let me bring up the notebook and section 3. Chapter 5.5, power and AC circuits. The reason I labeled it as 5.5 is because the book that I used, that we use for this class, has a combined as a subsection in chapter 5, which is AC analysis. So we are still working in the realm of complex numbers, and this will be complex power. Okay, so why are we interested in this topic? Well, we looked at power in resistive circuits, right? Chapters 1 and 2. Then we studied inductors and capacitors in chapters 3 and 4. We looked at energy transfer in chapter 4. And then we introduced AC voltages and currents in chapter 5. Now we're going to look at what happens when energy is transferred back and forth in an inductor and a capacitor. Okay. So electrical power is typically transmitted over long distances. You may have seen towers like these at least, several times in your life. There's one closest a few years ago. I was parking outside of Sprouts in Madonna Plaza, and I parked my car, and as soon as I opened the door, I almost missed hitting like this concrete structure. And I was like, what is this? And I look up and I see there's a long transmission tower right in the middle of the parking lot. So it's something that you never really think about it. Just it's part of our everyday lives. And you see long distance transmission lines coming from the south, going all the way north across the mountains. Right? That's how electrical power has been transmitted ever since it was invented. So electrical power is transmitted over very long distances. Sometimes these distances could be hundreds of miles long. Okay, hundreds of miles long. Now, the power is flowing from the utility company to the consumer. And consumers are of two kinds, residential and commercial, or residential and industrial. This is a big distinction when it comes to power or electric power. The reason is because most industrial customers have huge electric machines that run constantly, sometimes 24 hours a day, 7 days a week. Okay, these electric machines have coils, motors. Okay, those are inductors. So they have these huge inductive loads that are running almost nonstop. So as a utility company, they can see that there are huge inductive loads for their sources. When it comes to residential customers, not so much. The biggest load or energy load in residential environments are your washers, dryers, refrigerator, perhaps, and your HVAC unit, right? Washer, dryer, HVAC unit, heating, cooling systems. Out of these, the heating and cooling systems are the ones that would run, wouldn't run nonstop, but depending on the temperature and the settings, obviously, you'd be running them 24 hours a day. So on and off several times a day. Washers and dryers would have big inductive motors, but you might run it like maybe once a week, twice a week at most, and just a few hours a day at that. So as a residential customer, it's not as big of an inductive load to the utility company, whereas the industrial customers have huge inductive loads that run 24/7. And this is a problem because an inductor is a energy storage device, right? Inductor is an energy storage device. So the energy flows in and out of the inductor constantly when it's an AC voltage or AC current that's being applied to that inductor. Right? Industrial customers have inductive loads. Inductive loads have reactance. The reactance is associated with that stored energy. Okay. When you apply DC, what happens? Inductor receives the energy, stores it, and then releases it back into the circuit at a later point in time. When you apply an AC voltage or current, the energy goes into the inductor in the positive half cycle, and the negative half cycle, it flows out. Right? So there's a constant exchange of energy that is always taking place. Now, if it's example, it's a lab bench and you build a circuit, you build an RLC circuit, your source and your inductor are very close together. Okay. But when it's a utility company that's hundreds of miles away, the source is hundreds of miles away. I'm repeating the same thing, right? The source is hundreds of miles away. So what happens? If it's an inductive load, the energy is being transferred back and forth hundreds of miles or long distance transmission lines, right? So these transmission lines, these long distance transmission lines could be hundreds of miles long. And because you have an inductive load, the energy flows in and out of this inductive load all the time. That energy is associated with the resistive portion as well as the reactive portion of that inductor. So the power associated with the reactance is known as reactive power. Out of the three components, only the inductor and the capacitor are energy storage devices. They are the only ones that store the energy, hence they have reactance, and hence they have reactive power associated with that reactance. Resistive power is separate. Resistors do not have any energy storage capabilities, and so the power in a resistor is termed as real or average power. I don't prefer to use the term real power because it implies that somehow the reactive power is not real, imaginary. But as I stated earlier, reactance is not imaginary. It has a physical basis in real life. Hence, reactive power is also very real. It's only the mathematical representation because of the use of the complex numbers and the imaginary numbers that we term the resistive power as real and the reactive power as imaginary. Remember, we are still dealing with complex numbers. So real power, average power for the resistor is represented by the real number for the real portion, and the reactive power associated with the inductor and capacitor is represented by the imaginary number. Hence, it's a mathematical representation. So we term it as real power and imaginary power, but I prefer to use average power. Okay, so real or average power is associated with the resistor, inductors and capacitors associated with the reactance or reactive power. Okay, reactive power. Now, power is constantly flowing in and out of these elements, right? So, hold on. So power is constantly flowing in and out of the element. Now, when power is transmitted over long distances, what happens? Power loss occurs. Okay, power loss occurs. The power loss, again, power is V squared over R, or I squared times R, chapter 1, right? Chapter 1. Now, the power loss that occurs also is calculated using these equations. So if current is high, the power loss is the squared of the current. Okay. So it always, when power is transmitted over long distances, you increase the voltage as much as you can while keeping the current low. And again, goes back to that first power station that was set up. Remember, I stated in that talk where the first power station was set up with an average value of 100 volts to 110 volts. And once you have infrastructure set up to that voltage, you can't change it without it costing like trillions of dollars. Okay. And so North America uses 100 or 110 volts, whereas the rest of the world, which came later, decided to choose a higher voltage. For the same amount of power, you now, if you increase the voltage, you now only have to transmit lower current, which will save you money because losses are not as high. It's all tied together. Anyway, so coming back to our point, when power is transmitted over long distances, power is being transmitted back and forth. And because it is being transmitted back and forth, energy is constantly being exchanged in the inductive load, goes from the utility company to the industrial customer. And from that point on, it travels back and forth. Now, the more it travels, the more losses will occur. So the goal is to reduce that power loss as much as possible, right? We don't want it going back and forth all the time. So it's going to the load, going back to the utility company, back and forth all the time. The more it travels, the more it's going to lose. Now, real and reactive power does not mean that the company is sending two separate quantities of voltage and currents. Okay, the utility company just sends like one big piece. Let's say if it requires 10 units of energy, the utility company sends 10 units of energy, and then the industrial customer might use, depending on its requirement on that day, might use like 6 units for the resistive portion and 4 units for the inductive portion. Okay. But what happens is that those 4 units in the inductive portion will be sent back to the utility company. And then the next half cycle, it again goes back to the inductive load and then back and forth constantly. So for an inductor, what happens is, screen's messed up. Okay. As I was saying, what happens is, it uses some portion of the incoming current to set up its reactance in the magnetic field in the positive half cycle, right? For an inductor, let's say you are a customer and the switch is flipped for the first time, meaning the machine comes online and it requires a certain amount of energy. So when it requires a certain amount of energy, that inductor requires, the inductive load requires some power that is associated with this reactance. Some portion is used for the resistive, some portion is used for the reactive. Okay. In the positive half cycle, the energy flows into the inductor. Okay, positive half cycle, the energy flows into the inductor. This is when the switch is first flipped on. And now we are slowing down time. We have Dr. Strange on the job. Okay, he slows down time. And positive half cycle, energy flows into the inductor. Negative half cycle, what happens? Energy flows out and goes all the way to the utility company. Does that make sense? Right? Energy flows in and out. Now, if it's even a few miles away, instead of hundreds of miles, let's just say 10 miles, Even 10 miles is a long distance. If you remember, resistance R is L over A, directly proportional to the length of that conductor and inversely proportional to the cross-sectional area. So if you take like a 10-foot section of a conductor, long distance transmission lines are like really thick, but in reality, compared to the length, it's small. So even if you take, let's say, a small piece of that miles long conductor, it'll have a resistance of a few ohms perhaps. But when it's tens of miles long, that resistance increases. And that resistance of that conducting wire causes transmission losses. So in the positive half cycle, when the switch is first flipped on, the utility company sends some energy to the inductive load. Some of it is lost during transmission. Most of it reaches the end, but negative half cycle, it flows back out and goes to the utility company. This second portion of the negative half cycle, where the energy flows out of the inductor and goes back all the way to the utility company, is needless, right? There is no purpose to it. It's just sending it back out to the utility company. And then the next positive half cycle, you again require the utility company to send it back to the inductor. And again, some travel loss will occur, transmission loss will occur. And this happens 60 times in 1 second. That is, if it's a low transmission frequency of 60 hertz, it still happens 60 times in 1 second. So imagine 60 times in 1 second and 24 hours a day, if the energy is being transmitted back and forth, how much loss would occur collectively? So let's take a pause while you think on that. Let me know if you have any questions. Any questions? Has it been making sense so far on what what I'm trying to talk about, right? Okay. All right. So what happens? We don't want that energy to be transferred back and forth constantly. So what do? Well, fortunately, we have a device that is the exact opposite of an inductor, which is the capacitor. Capacitor works exactly the opposite, meaning it is an energy storage device, so it's very similar, but it behaves exactly opposite. When the energy flows out of the inductor in the negative half cycle, the capacitor actually absorbs energy or stores energy in the negative half cycle. Okay, so when the energy flows out of the inductor, instead of traveling all the way back to the utility company, if you place a capacitor right in front of that inductive load, meaning the industrial customer places a capacitor right in front, the energy, instead of traveling all the way to the utility company, now gets stored in that capacitor, which is local. It does not have to travel long distances. Make sense? And from that point on, the energy that is required by the inductor is now supplied by the capacitor. The energy is bouncing back and forth locally between the inductor and the capacitor. Okay. So the stored energy in the capacitor is sent back in the positive half cycle. In the positive half cycle. So let's say the utility company sends like 10 units of energy. The inductor requires like 4 units of reactive power. And when it sends it out in the negative half cycle, the capacitor absorbs that 4 units. And from that point on, those 4 units are now supplied by the capacitor. So the utility company does not have to send 10 anymore. It only sends 6. So your power requirements are now reduced. And this process, of course, the energy bounces back and forth between the inductor and capacitor. And this process has a term, which is what we are studying in here, is known as the power factor correction. So designing and choosing a capacitor to balance out these power requirements is known as power factor correction. Okay, power factor correction. And you actually did a little bit of that in lab 7, or at least those of you who are taking the lab. And I'll explain how and why. This is, by the way, also the topic for lab 8. Power factor correction is the topic for next week's lab. Okay. So power factor correction is a new term. We also introduced the term of total complex power. And total complex power is the average power plus the reactive power. Okay, average power plus the reactive power. All right, any questions so far? Let's take a pause. You think on all of that, and let me know if you have questions. Yeah, go ahead. Okay, no questions, I guess. Okay, so think back to lab 7, or if you're not taking the lab, think back to chapter 6, resonant circuits. What happens there? At resonance, what we said was the impedance of the capacitor and inductor are exactly the same in magnitude, but opposite in phase, so they cancel each other out. So output across the resistor goes to maximum. Okay, that's one way of looking at things. The other way of looking at things is energy based. Let's say your source is supplying 10 units of energy. Now I'm not using, like, I'm just using general lay terms. Okay, I'm not using like volts, currents, amperes, watts, nothing. Just let's say it's sending 10 units of energy. Your circuit has R, L, and C. You're taking the output across that resistor. You're sending 10 units of energy, depending on the circuit frequencies and the values of the components. Some portion goes to the inductor, some portion goes to the capacitor, and some portion goes to the resistor. Make sense? Right? Now the inductor receives the energy in the positive half cycle, sends it back out in the negative half cycle. Capacitor receives the energy in the negative half cycle and sends it back out in the positive. So if you have both a capacitor and an inductor connected either in series or in parallel, doesn't really matter how it's connected, then the energy flows out of the inductor and goes into the capacitor. So out of those 10 units of energy, let's say they each take like 3, 3, and 4 units. Okay, 3, 3, and 4 units. But at one particular frequency, the energy of the inductor and the capacitor is perfectly balanced. And the energy coming out of the inductor goes into the capacitor. And then when the inductor requires certain energy, it takes exactly the same amount from the capacitor. And they're both equal and opposite. So whatever energy is required between the two is now bouncing between the two of them. So if the source is sending 10 units of energy, once the switch is flipped, your system reaches steady state, and the inductor and the capacitor do not need any more energy from the source. They're just sending each other energy back and forth. Then the 10 units of energy all goes to the resistor. That happens only at one particular frequency, and that is the resonant frequency. For all other variations or all other combinations, the 10 units of energy, one unit might go to the inductor, another might go to the capacitor, so your resistor might have 8 or less than 10. But at that one particular instance, one particular frequency, that is the resonant frequency, the inductor and capacitor are perfectly balanced. The energy requirements drop to 0. Everything is sent from the source to the resistor. And that is a perfect example of a perfectly balanced power factor corrected system. Okay. So there are multiple ways to look at a system. So this is another way of looking at it. In real life, it is never possible to get a perfect balance. And the reason, of course, is because the inductive load will vary throughout the day. From minute to minute, from second to second, it will vary, depending on the speed, depending on the values of the components, depending on how many machines that consumer is running. Okay. But the goal is to reduce the requirement of the reactive power from the utility company. So power factor correction is an entire expertise or expert field by itself. Right. Let's take a pause because before we go into the equations. Hope all of this made sense, and then let me know if you have questions. Yes. Bandwidth. That is only if you're using it as a filter. So the question being asked is, do we want to minimize the bandwidth? And yes, the answer would be yes, but that is only if you're using that circuit as a filter. In this case, we are not using it as a filter. Yeah. Yes. Yep. But that was for filter circuits, because in this application, for power factor, like when we're studying AC power, our frequency does not vary, right? The source utility company is sending, let's say, for instance, is sending a signal at 60 hertz, then it's only going to stay at 60 hertz. It's not going to change a lot from that value. So the resonant circuits and the power factor corrected circuit, there, again, it's the same technically it's the exact same circuit, but the applications are different. So what we are studying in both is a little bit different. But what I was pointing out was that at resonance, the energy is perfectly balanced between the inductor and the capacitor. So it's 100% power factor corrected system, which is not possible in real life for an inductive load at an industrial customer. Okay. All right. Any other questions? Okay. So this is the first set of equations. All uppercase letters. P still stands for the power that is associated with the resistors. And it is the average power still noted with watts, okay, W watts. The new term we are introducing is Q, which represents reactive power. And reactive power is associated only with reactance, meaning only inductors and capacitors. Okay, resistors do not have reactive power. Only inductors and capacitors have reactive power. The units for reactive power are different. It's volt, ampere, reactive. Okay, volt, ampere, reactive. Okay. And then P and Q summed together gives you the total complex power. Remember, P and Q are just mathematical representations. When the utility company sends something, it's simply sending voltage and current. Okay. How it is used and what fraction is used for real and what fraction is used for reactive power is up to the end consumer. Okay. Utility company simply sends the voltage and current. So when you have P and Q summed up together, you get total complex power, which is represented by the letter S. They just went in alphabetical order. Okay, real power or average power was P, so they chose Q for reactive, and then R is reserved for resistor, which is one of the most fundamental units of electrical engineering, and so skip R and went to S. And because we are using complex numbers, meaning real and imaginary quantities, it's P plus JQ. Reactive power, like reactance, is represented with the imaginary number J. So P plus JQ gives you the total complex power S. And the unit for total complex power is volt ampere. Volt ampere. Okay. These are the first set of equations. These equations may be new, but the structure of these equations is exactly the same as what we have learned so far. That is in rectangular coordinates. P is on the real axis, Q is on the imaginary axis. And so, similar to the impedance, similar to the phasors, we have a triangle, and the triangle is known as the power triangle. Okay, it's the power triangle. It's still the same thing that we have seen, we have studied previously. Okay. Real axis has the average power. So real axis, RE. And then you have the imaginary axis. This is for the inductor. Remember, the inductor, the impedance is plus 90. And for a capacitor, the impedance is minus 90. So the reactive power for inductor is pointing straight up, plus 90. For a capacitor, it is pointing straight down. Okay. This is QL, PL, theta L. This is PC, QC, and theta C. This is for capacitor. Okay. P and Q form the two sides of a right angled triangle. And the angle it makes due to the length of Q gives you the power angle theta. For an inductor, of course, the power angle is positive. For a capacitor, it's negative. It goes in the clockwise direction for a capacitor. Same concepts as AC, the vector analysis we did for chapter 5. Now, because it is a right angle triangle, 4 quantities, if you have any 2 quantities, you can find the other 2. And so the first set of equation comes from there. The hypotenuse is simply the product of the voltage and current, the RMS values of the voltage and current. And that's how we get the equations for P and Q. Okay, that's how we get the equations for P and Q. P is the real power, is VRMS, IRMS cosine theta, and Q, VI sine theta. This, of course, is only for a resistor, and this is for inductor and capacitor. Comes from trigonometric identities. Theta is the power angle. It is also the difference between the angles for the voltage and the current, V minus I. It is also the same as the impedance angle. Remember the impedance triangle. Z is R plus JX. And there too, impedance is V divided by I. So theta V minus theta I gives you that impedance angle. For a inductor, that impedance angle is positive. ZL is always plus 90. ZC is always minus 90. Hence, QL is plus 90 and QC is minus 90. But what is happening in real terms? In real terms, you want your QL to be as small as possible. If this is your P, if this is the P of your system, and this is the required Q, yeah, this is the required QL. Now your angle is quite large, right? This theta this is quite large. If you place a capacitor in front, the requirement for QL goes down. So now QC brings it down because it points straight down. So your end result is quite smaller. So now your theta, required power angle, is small. And your total required power from the system would be QL minus QC. Reactive power pointing straight up, capacitor power pointing straight down. So again, energy bouncing back and forth between inductor and capacitor. Mathematically, it's QL minus QC. You could never get QL exactly equal to QC, or actually the other way around. We can never get QC exactly equal to QL because QL is always fluctuating. Okay? Depending on the time of day, depending on how many machines are running, depending on the loads and the values of those components. Okay, but that's the goal. The goal is to get QL as close as small as possible. And that is known as power factor correction. So what is power factor? Mathematically, we describe it as the cosine of that power angle. Remember, right angle triangle, right? Right angle triangle. Cosine of theta means we want that angle to be as small as possible. We want the cosine of that angle. We want the angle to be as small as possible, so the cosine is as large as possible. Okay. Ideal theta or ideal angle is of course 0 degrees. So cosine of theta would be cosine of 0, which would be 1. That is the highest possible value of that power factor. Highest possible value. It is also, not also, it is stated in percentage. So cosine of 0, which is equal to 1, is 100%. Okay, 100%. Cosine of 0 means your QL and QC are exactly equal. Of course, real life, it is approximately 90% or so. Okay, 90% or so. For the power factor, we also use one more term to describe it, to describe the load, and that is lagging or leading. And that lagging or leading comes from the fact it tells you the status of the current of the system with respect to the voltage. Meaning your voltage is your reference and you're stating whether the current leads or lags. And this is relatively straightforward to remember. For an inductor, the voltage is ahead of the current by 90 degrees. Eli the Iceman, remember? So if voltage is my reference point, I have to state the current lags the inductor. The current lags the inductor. So if we state power factor is lagging, then it refers to an inductive load. In a capacitor, the current leads the voltage by 90 degrees. Right? So V minus I is minus 90 degrees. But I is ahead of the voltage. It's leading, meaning if you state power factor is leading, it's a capacitive load. So if current lags the voltage, it's lagging. If current leads the voltage, it is leading. And this is fixed. Inductive load is lagging always. Capacitive load is always leading. That doesn't change. But the utility company needs to know this because the customers will describe, okay, my power factor is 90% lagging. And what that means is that the utility company has to send a certain amount of power, okay? So the industrial customer, if the power factor drops below a certain percent, the utility company is not going to send it any power. It'll say, you need to get your power factor up before I send you anything. As a real life example, and again, this is a very simplistic example. Let's say the utility company is designed, the infrastructure for the utility company is designed to send 100 units of power, 100 units of energy. Industrial customer has 10, sorry, not 100. Let's say utility company is designed to send like 40 units of power, 40 units of energy, okay, maximum. Any more, it needs to have the transformers, the generators, and the power transmission lines to handle all of that unit, which is very, very insanely expensive. So it's not going to do that. So it says my infrastructure can handle 40 units of energy. Tell me what are your requirements. Industrial customer says I have 10 machines, each requiring 10 units of energy. Okay, out of those 10 units, maybe my inductive load requires like maybe 6 or 7, let's say 7, right? So the company would say, okay, fine, you turn on machine 1 for now. When it turns on the machine 1, utility company, which has the capability to send 40, will send 10 units of energy. Consumer receives 10 units, 3 units go into the resistive portion, 7 goes to the inductive portion. After that, the local power capacitor sends the 7 units to that first machine. So from that point on, the machine only requires 3 units of energy. You guys with me so far? Make sense? Then the company will say, flip on the second machine. So customer turns on the second machine. Second machine again requires 10 units of energy. You send 10 units of energy, and then staggered approach to turning on one at a time. So when the power goes out, if there's a blackout in an industrial area, the customers cannot flip on all the switches all at once. They have to work with the utility company to create a staggered turn on. If power goes out on campus, if there's a total blackout on campus, campus is huge, requires a huge amount of power. There's a staggered turn on. Okay, the power goes out entirely on campus. The central plant and the facilities, facilities managers, they work with the utility company to create a staggered turn on, meaning power comes on one at a time in all the buildings and all the places. If you turn on power all at once, the utility company cannot supply all of that energy. It will say you have to get your power factor up before we send anything to you. Okay, that's what happens in real life. Okay, few more equations, and then we'll be done for today. The hypotenuse of the power angle represents the magnitude of S, right? Magnitude of S and the power angle theta. And that magnitude of S has a term, apparent power. It's simply the product of the voltage and current, RMS values, VRMS times IRMS. Remember, these come from the equation from chapter 1. Power is the product of voltage and current, and voltage is the product of current and resistance. V equals IR, Ohm's law, and power equation P is VI. Okay, so all of those equations come from there. So from the right angle triangle, we can state total complex power as a magnitude, and it has phase, that is a power angle. Then these equations come from P equals I squared times R as the exact same structure. This refers to the resistor. These refer to inductor and capacitor. Okay, the structure is the same. Q is I squared times X. And everywhere we use RMS values. So, instance, if you're talking about the inductor, then QL can be found from its current times XL. If you're talking about capacitor, QC can be determined from IC RMS square times XC. And if you have voltage, it's V square over X. Okay, that's where the equations come from. Okay, so as I said, equations and quantities and the terms are new, but the structure is exactly the same. The structure is not different. And there's one final equation. S, the total complex power, can also be given by the product of voltage and current. And these are in phasor form. The voltage and the current are in phasor form. It's half VI asterisk. And that asterisk notes that it is the complex conjugate of the current I. Okay, so I'll write this down. The asterisk notes that is the complex conjugate of that quantity. It's a complex conjugate of I, not V. So V is just that. I asterisk is just the complex conjugate of I. Complex conjugate simply means that the position of the real portion, the imaginary portion, is flipped around the real axis. So A plus JB becomes A minus JB. And vice versa, obviously. Okay. And then R with the angle of theta is R with the angle of minus theta. So if it's positive above the real axis, then it goes below the real axis. Angle is flipped or the imaginary component is flipped. Okay. That's what it means, complex conjugate. So we'll end class here today. There's only 4 or 5 slides of information, but there's a ton of new information in here. So please review this information. Take 10 minutes, 15 minutes, think back, reflect, and then if you have questions, reach out to me. There are 2 examples. We'll look at both examples in next week. And then the week leading up to the final, meaning next week and the week after that, we will simply do in-class activities and exercises, going back to chapters 1, 2, 3, and 4. Okay. As I said, quiz 8 is on Tuesday, which follows a Monday schedule. Monday is a holiday, so we'll meet Tuesday and Wednesday. Tuesday will be the quiz 8. That will be based on chapter 6, filters. And then quiz 9, which will be in the last week of classes, will be on AC power. It's the examples we'll cover on Monday and, we'll cover on Tuesday and Wednesday of next week. And one final homework also based on AC power. And I will not assess AC power on the final exam. So that is your only shot at doing that. But it'll be a big quiz. Yes. The AC power or the resonant circuits? No, it's probably 20. So that'll be, you know, so it depends on the topic. I don't know what I don't know from the top of my head. I can look it up right now. It's AC power, then it's only due after we finish the examples. But again, as usual, get started on the homework, as and when you have the time. There are some concepts in there that you should be able to answer. And then if it's actual examples, we can, take care of those later. Okay, so that will be, I'll make that due after we get done with the power. So probably next Thursday or next Friday. Yeah. Let me see. The resonance circuits in 18, 19 was due yesterday. Yeah, 20 is due on Sunday. So I'll postpone that. Okay. All right. All have a good weekend. Relax if you can.